Starting recording for everybody who's not here. Okay, so if anybody else comes in, I will try my best to mark attendance as they come in. So this week marks the first week of you don't have a packet. So if you noticed, I am now attaching both PDF and Google Doc versions of everything because some people can and like to print. Some people cannot and want to be able to type into a Google Doc for their notes. And some people want to just kind of absorb, take some notes on paper or take photos of what I'm doing and go back and deal with it later. All of those things are acceptable. Remember, notes are notes. They're your notes. They are not part of any graded assignment. I think I've given you enough small little chunks of graded assignments. But anything that I've provided to you as notes is the actual thing I will be writing on in class. So that's how you know that's what we're going to do. So today I actually am going to do a couple of demos, which is kind of the case with these chemical reaction stuff for the next couple of weeks. I'll be doing a lot of demos in class so you can still kind of see stuff as we go along, and I'll go over at the end of class the actual specific assignments that you need to do for me this week. So there was an actual long full page warm-up reading all about Antoine Lavoisier, but I just kind of wanted to go over this this part in the middle, which was the actual most important part of that reading. And that's kind of like what Lavoisier did. He was basically what we consider to be the father of chemistry, because he started measuring stuff. So his original job around the time of the French Revolution was actually to make gunpowder, which is kind of cool, but also very, very dangerous. And gunpowder is a mixture of like charcoal, of carbon, and of the substance called saltpeter. And saltpeter, it does say down here somewhere in the text, what does it say the actual name of saltpeter is? First paragraph.
Potassium nitrate.
Potassium nitrate. Okay. We just finished going up over this stuff. Potassium nitrate. Does that sound like an ionic or a covalent compound?
Ionic.
It is ionic. Okay. So what is the symbol for potassium?
K.
K.
Yeah.
What's its charge?
+1.
+1. Okay. Nitrate, is that the element nitrogen or is that a polyatomic ion?
It's a polyatomic ion. That
Yes.
stuff.
Yes, it is. So you have that. Its formula is this, NO3. Keep its prophylactic parentheses. The charge on that thing is a -1. So if that's the case, what's the formula for potassium nitrate, for saltpeter? If I've got a +1 and a -1.
KNO3.
KNO3. Yeah. Good job. Okay. So it's KNO3. So that's saltpeter. So it's this bold part I want to make sure we read. So it said, characteristic of Lavoisier's chemistry was his systematic determination of the weights of reactants and products involved in chemical reactions, including the gaseous components, all right? Gaseous referring to just gases, and his underlying belief that matter would be conserved through any reaction, otherwise known as the law of conservation of mass. That is the entire focus of today's class. So, what do we think a reactant is? not in like specific chemical terms, but just in general. What is a reactant?
Something that reacts to other things.
Okay, so it's going to react to other things. It's going to react with itself. And do you think in a chemical reaction, these are the things we start with or the things we end with?
And
And with.
Ooh.
Baskin?
Oh, I think start. I think
gonna be start.
Because you can make
Because how else are you going to react things together unless they're there at the beginning? So reactants are materials you start with. Okay, so these are materials. So
Ms.
hard
Bass-
to write. Yes.
I just want to let you know that I'm here. I'm just with Taeyeon. So just
Okay.
for,
Way to not be social distancing, guys. Uh-huh.
You add.
Whatever.
Oh, Malachi.
Oh my god.
Who's that? Is that Sahara?
You know that's
Oh,
James.
Sahara!
It's Sahara. Hey, Sahara.
I'm muting you. You're being annoying. We're doing stuff. All right. So these are the materials you're going to start with, which means our products are going to be what you end with. And in general, what does it mean if stuff is conserved?
It's like saved or like
It's saved. All right. So in general, we're saying it's conserved. So right now, before Lavoisier came around, people didn't actually measure things. They just mixed stuff together to watch what would happen, which while is kind of cool, you don't learn as much. So Lavoisier was the first guy who said, no. I am going to take my reactants, my starting materials, and I'm going to actually measure how much I have. And then I'm going to do a reaction, and I'm going to measure my products, how much stuff I made. And what he found was that the amount of stuff you start with was always the amount of stuff you ended with. The thing that kind of is a little bit problematic for some people was that he was the first one to include gaseous components, meaning gases. Do gases have mass?
No.
yes.
Yes, they do have mass. Is it easy to catch a gas and put it on a balance?
No.
No.
No, that's the problem. So that's actually kind of what we are going to talk about and address today is how do you actually capture the mass of a gas and make sure that you know that that is there. So, okay. So moving on. So we're gonna do these notes, but first I wanted to do a couple of demos of actual chemical reactions to kind of see what it looks like when you don't capture mass. So let me switch to come on. Okay, and hold on. Okay, so does everybody see that? My balance here. Woo! Make that up a little bit. Okay. So if I put this little candle on my balance, what does the mass read on the balance?
92.1. Oh.
10.26.
10.26.
10 point.
It's upside down.
Oh, yeah.
Yeah.
That's okay.
Is that easier?
Yes.
Okay.
Yeah.
Okay, so the mass of the candle is 10.26. So if I light it, what is going to start happening to the mass of that candle as it burns?
It's gonna increase.
Go away.
It's gonna decrease.
It's going to decrease.
Oh,
It's already decreased a little bit. Am I violating the law of conservation of mass? Am I making mass disappear?
No, it's just going somewhere else.
Yeah, in a way, yeah. That
Well, it's going away from this physical, hard, solid candle, but where is the mass going?
away.
In the air.
In the air, right? It's going up here in the air. So the candle is releasing some sort of gas. You can kind of see that if you imagine when you're looking at a candle, you can see gas and stuff coming off. It's even easier when I blow it out, right? You can see all the smoke and stuff coming off. You know that that is mass coming off of the candle. So it's not that I have made mass disappear. It's not that I have violated the law of conservation of mass. It is that I just did not create a system that captured it all. That's the difference. So that's one thing with a candle. But let's do something else. Let's take a beaker, and I'm going to put some vinegar in it. Just a little bit. Ooh. So if I put a little bit of vinegar in a beaker and I add some baking soda, I'm seeing the same thing. I'm seeing my mass slowly decreasing. Because where is that mass going?
up into the air.
It's going up into the air. You see all those bubbles in that beaker? All those bubbles are indicating that you've got some sort of gas going on, and the gas is escaping. So if we want to be able to prove the law of conservation of mass, we have to figure out some way to actually capture that gas so that we can measure it and so that we can actually do our proof of things is kind of how this is going to work. So let me switch back to my iPad now. Okay. So these are now working off of the notes. So the bolded sentence that we talked about before was this: reactants, weighing reactants and products, including gaseous components that matter it's going to be conserved or saved. So the law of conservation of mass. So when we mix the baking soda and vinegar, what is it that we just saw? What's the main visual cue when you mix those two things?
Fizzing.
Fizzing. All right, so you got fizzing, you have bubbles, all right? That's what's coming off. So is this a chemical or a physical reaction, going back all the way back to Unit 1?
Chemical.
It is chemical, and how do I know? What is my clue?
Fizzing.
The fizzing, right?
Because it can't be undone.
All right. The fizzing tells me a gas is formed. Gas being formed was one of the signs of a chemical reaction. Okay, so I know that. Okay, so this is the actual chemical reaction of baking soda and vinegar. So acetic acid is what vinegar is. And sodium bicarbonate is what my baking soda is. So in this instance, what are my reactants?
Vinegar and baking soda.
The vinegar and baking soda, these are my reactants. So that means that the sodium acetate, which acetate is a polyatomic ion we didn't cover, and that's fine. So the sodium acetate, the water, and the carbon dioxide are my products. Which one of those things gives me the fizzing?
Sodium.
It's going to be one of the products.
Oh,
Water.
The fizzing is a gas. So which one of those things is a gas?
carbon dioxide.
The carbon dioxide. So the carbon dioxide is a gas, and this produces the fizzing. Okay. This is actually why you add baking soda to your baked goods, because you want to make the carbon dioxide inside the baking process, and it's actually what makes your baked goods light and fluffy. Like that's what creates the air bubbles in a cake or in a something like that. It's the carbon dioxide from the baking soda. Okay, so I'm starting off with my reactants, and then I have my products. So what do we think this arrow in this reaction here indicates?
Wait, Ms. Bass, can you repeat your question?
I'm just asking question number 4.
Oh.
What does the arrow indicate? I have reactants, and then I have products. There's an arrow in between them. What do we think the arrow indicates?
It's like transition.
Like the process?
Yep. All right. Transition is a good way to think of it. Transition from reactants to products. All right. It is the change, right? It's indicating that a change occurs. Okay. So the law of conservation of mass tells us that all the particles present at the start of a reaction will be present after the reaction. Is that true in this little diagram? The easiest way to do it is to literally kind of count up little circles. So that's what I'm going to do. So I see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 things over there. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 13 things there. So we did, right? Yes, there appear to be the same number of each element or particle on each side. Matter was conserved. All right, that's what it means to have matter be conserved, is that you have the same things. So we're going to do this reaction again, and I want to think about how we are actually going to measure the mass of all of these things. So vinegar is a liquid. How can I measure the mass of a liquid without it running all over the table?
Put the cup on the weight, then refresh the weight. That way it's to 0, and then put the water in it.
Yep. Okay. So it's called tare. So we're going to tare the mass of a cup, then add the vinegar. That is what you do with any sort of liquid. Okay. And What about the baking soda? The baking soda is that white powder. I don't just want to put white powder on the balance.
Do the same thing.
All right. Basically do the same thing. Okay. Now, when you mix those, we saw that there was a liquid and then there was the gas. All right, the gas being the carbon dioxide fizzing out. If I do this in some sort of cup or something, this mixture is basically still in the cup. That's fine. How are we going to measure the mass of carbon dioxide? How are we going to capture the gas? What are some ways we can use to capture gas?
Put a lid on it.
Put a balloon on it. That is exactly what we are going to do. We're going to put a balloon on it. So I'm about to switch pages. So if anybody needs to take a picture of what's on the screen, do it right now. All right, moving on. Okay. So if we were in school, I would have you do this. I would give you some stuff and I'd have you figure this out. But we're not. So instead, I'm going to do this and we're going to all write down the data. So I've got a balloon, a flask, baking soda, vinegar, and my balance. There's the procedure that you see. And here is a data table. Okay. So I am going to I'm going to switch it back onto my document camera so we can see what I'm doing. And you guys are going to fill out your data table. I will do my best to write it down as we go between steps, but I'm about to switch off of this screen. But we're going to measure the balloon. We're going to put the baking soda in the balloon. We're going to measure the flask. We're going to put the vinegar in the flask. And then I'm going to try and carefully attach these two things without dumping the baking soda in. And then we're going to try and see what everything is. Cool? So, cool. Okay. All right. So step 1 says measure the balloon. So let me turn my thing on. Okay. So the mass of my balloon, oh, how convenient, is exactly 3.00 grams. So, oops, and then it changed. We'll stick with the 3. Okay. Then it says measure the balloon with baking soda. Okay, so I'm going to attempt to use a funnel to put baking soda in without getting it all over. We'll see how this process works. I anticipate I'm going to get baking soda all over my jeans. That's okay.
I believe in you, Miss Basket.
Okay. All right, that's not too bad. Okay, so now I've got baking soda in my balloon. So it now weighs 5.29. So if I started off with a balloon of 3 and my balloon with baking soda is 5.29, what is the mass of just the baking soda?
2.29.
2.29. All right. So I've got my baking soda ready to go. Now my Erlenmeyer flask, it's a nice pretty little one. It's not small, it's a big glass thing. So 81.63. And my jug of vinegar, well, it's one of those giant Costco jugs, so I have to do this a little bit away from the camera. All right, so I'm going to put some vinegar in here. Ooh. Okay. Okay, so my vinegar, 102.50. So how much vinegar did I add? I'm going to use a calculator. My calculator says that would be 20.87. So in theory, I have 2.29 grams of baking soda and 20.87 grams of vinegar. And if I add those two numbers together, I have 23.16 grams of reactants. That's how much I have. Okay, so here we go. So let's see if I can very carefully.
Miss Baskin.
Yes.
Wait, what was it when it was empty?
Let me, before I do this, you're right, let me switch back over. I wrote everything on my iPad. Bam. Okay, so it should be mass of the balloon was 3.00, mass of the flask, 81.63. Okay. All right. Everybody got those numbers now?
Yeah.
We'll go
Wait,
back. We'll go back to this screen, but
Wait.
yeah.
Okay, never mind.
Okay. Okay. So now I've got my balloon and my flask here. I'm gonna have to raise this up because otherwise the balloon is gonna inflate into it. All right, and let's dump.
That's cool.
Okay. So I gotta kind of move this so we can. All right. So that reads 107.41 is how much this whole thing was. And you can see like that's not a ton of gas here when you look, but it did inflate it, right? So 107.41. So now let me switch back over. Stay with the iPad. Okay. So from the 107.41, we need to subtract off these two things because that's equipment. I don't care about that equipment. So I've got 107.41 minus 3 from the balloon, minus 81.63 from the flask, and I get 22.78. So I've got this number and this number. I went from this to this. Are those the exact same number?
Mm-mm.
They're not, but did I destroy matter? Did I actually make matter disappear?
No. No, you didn't.
No.
Just do it. No? You just transferred it.
Okay, so those two numbers have a difference of 0.38 grams. So what are some possible reasons that they might be 0.038 grams different? Thinking about what I just did, where could 0.038 grams have gone?
because you shifted the weight using the balloon.
Okay, so whoops. All right, so it could be because I move objects on the balance is where I could have lost some stuff. Where else? Are balloons perfect gas catchers?
Mm-mm.
No?
Oh, some escaped.
All right, so some CO2 escaped the balloon. So would we say that we mostly did a pretty good job of proving that matter cannot be created or destroyed? Did we do a pretty good job?
Yep.
Yeah,
Yes.
we did a pretty good job. So I would say that, you know, in conclusion, we were able to show that matter is conserved in this experiment. Our evidence is that our reactants had a mass of 23.16 grams. The products had a mass of 22.78 grams for a difference. Remember, difference means subtraction. So for a difference of 0.38 grams. And I would say for a difference of only 0.38 grams. That is a small number. So in my reasoning, I would say the small difference in mass is not due to destroying matter, but rather not accurately capturing it during the experiment, right? And we just thought of some ways where we might have not captured some of that mass. So the important take home here is that the law of conservation of mass is a law. You cannot violate the law. If you think you violated the law, it's because there was something wrong with the experiment, not that there was something wrong with the world of chemistry. Okay, so it means most of the time, it means that you missed some gas. It is gas that makes the law of conservation of mass tricky because it is difficult to capture gases. Most of the time we have to do it in a balloon or do a reaction in a completely enclosed space to be able to capture all of the gas. So I'm about to switch back to the slide deck. So take a picture of that if you need to really fast. Everybody good? Okay, so, whoops. What is due by Sunday of this week?
Ed puzzle.
Ed Puzzle video 32. That video is on this law of conservation of mass. It does explain it again. Again, the Edpuzzle videos are part of your participation grade. I am now basically giving them a completion grade, which means you should not stress about doing them. You should just get them done. The exit ticket, which will be on the next screen, or if you're watching this on video, you need to use the link that is in the description directly below this video. Completing the exit ticket is the other half of your participation grade. So your participation grade, there is literally no reason for it not to be a 10 out of 10 because the Edpuzzle is a completion grade and doing the exit ticket just requires you to do the exit ticket. So those are completion grades. Next, the quizzes for this week is your practice. And it is also a completion grade this week. Last week it was for accuracy. This week it is for completion. If you do the law of conservation of mass quizzes, regardless of what percentage you get, if you do it, you get a 5 out of 5 for that portion of the grade. The one thing I am grading for accuracy this week is the conservation of matter Google Doc assignment that is attached to the week 2 practice and application assignment in Google Classroom. That's why I've been pushing so hard to get everybody in Google Classroom, because that you will start having assignments there. So it is 2 short questions. You should look at these notes, go back and watch this video if you need to, or pop in and ask me any questions if you need to, but that is the one thing that you need to do that is based on accuracy. However, here's the way percentages work. The law of conservation of mass Edpuzzle is completion. The exit ticket is completion. The quizzes is completion. This is the one thing that is not. There's 4 things. 3 out of 4 are completion. So you can get a 75% for your week for just doing completion assignments. That's the case every week. I set it up that way. Nobody should have a grade lower than 75 because you don't even have to do the accuracy thing every single week and you can get a C. Are we clear?
So where's the Google Doc? Because I just went to the term for week 2, like both of the participation in practice and application, and like the only thing in there is the quizzes game link and the Edpuzzle link.
No, it should be there. Because I had it made one for you. So
Oh, okay.
You see it?
Yeah.
Okay.
Thank you.
I was about to say, because when I look, it looks like this. You should have those 2 things. And it may have already made an account for you for that doc. So that should be there for you.
Okay.
Okay. Okay. So the last thing you need to do is your exit ticket. There it is. And I can write that into the chat as well. And again, for bit.ly links, if you don't do the capitalization correctly, it won't work. So it does have to be a capital C on that Chem. And that's it. So once you get that exit ticket written down or pulled up for yourself, unless you have any questions, that's it. That's the end of class. The other thing I will say is everything, I am accepting work no matter when this advisory. So if you did miss something last week, just go back and do it. I'm doing grades on Mondays and then I'll update grades again on like Wednesdays and Fridays. So if it's been like maybe 3 days and you do something and it's not reflected in Aspen, send me a note. But otherwise I am going back and checking all of the old work periodically and updating your grades. So if you didn't do something, go back at a later date and do it so you can get the credit. All right, so I'm gonna stop recording and then